This is a presentation on a project that was originally done for the CSEP 573 Applications of Artificial Intelligence course, winter quarter 2022. My name is Derek Vetchern, and the project is Reward Allocation for Reinforcement Learning in Collectible Card Game Drafting. The motivation for the project was to explore reinforcement learning, and in particular in the domain of collectible card games. There are some reasons why it's an interesting topic. There is imperfect information. Rewards are sparse and delayed. The action space is very rich and heavily dependent on natural language descriptions that either fit keywords or freely written text that needs to be interpreted. There are complex interactions between decisions and effects, and there's even multi-phase strategy. The strategy that goes into deck building and into an individual battle. Now, the classic game here is Magic the Gathering, but it has been shown to be Turing complete and is far too complex of a target. Also, there isn't an open source implementation of the game that could be used to train an AI against, and implementing it is completely out of scope. So instead, I found research that a Brazilian master's student did on implementing a simplified card game that is intended for facilitating AI research, and then applying reinforcement learning to the drafting phase of the game. So let's look a little more at the problem definition. In a collectible card game, you're going to have some sort of battle where two players have hands of cards, a library they draw from. They play resources and spells and try to attack each other and reduce the opponent's life total to 0. Before the battle, there is deck building. There are various formats for this, but one common format in tournaments is drafting, where a group of players sit around a table and have a collection of boosters, which are small packs with, say, 15 cards in them. And each player opens a booster and selects a card from those choices and then passes it on. And so you build your deck on the fly, given limited choices, and you don't know what your next set of choices will be, and your choices affect the choices of the other players. So there's a lot of strategy that goes into drafting as well. And this project is focusing on the task of drafting. In particular, learning a drafting policy for a fixed battle agent, because an effective policy will differ depending on the strategy capabilities of the agent. Now, for this environment, the drafting task is somewhat simplified. The agent is presented with a choice of 3 cards, of which they choose one, and then they will not see those cards again as another choice, and the opponent is presented with the same choices, but their choices are independent of each other. So the agent selects a card, that becomes the first card in their deck. They get a new set of 3 choices, select a card, the second card in their deck. They repeat this process until they've constructed an entire deck. Then, to evaluate the agent's performance in constructing a deck, a single game is played, and the outcome determines the reward, plus or minus 1. In this case, I was using the max attack agent, which is a fairly simple agent that uses a heuristic. And then, for the case of this work that I was replicating, where a proximal policy optimization algorithm was used to update the agent to grossly oversimplify things, the attribution of the reward is decayed exponentially backward in time. That's not exactly what happens, but that's roughly the idea behind it. So what are some of the limitations to this approach? The first one is if we look at what happens between the drafting decisions that constructed the deck and the battle that determines the reward for those drafting decisions. Very important step happens. The deck gets shuffled, which means that the order that the cards were drafted is no longer the same. So the agent begins a battle, draws the first card off the top of the deck, takes some additional actions, continues drawing cards and taking additional actions, and at some point wins or loses the battle. You'll notice that there are still some cards left in the deck that never were drawn. So those original drafting decisions never actually came into play in this battle. And yet we're still naively allocating award to those decisions. So first limitation is we're doing value updates for undrawn cards where we didn't actually learn new information. The next limitation is, again, going back to how the order differs. We shouldn't be allocating reward based on the time proximity to the final drafting decision. We should be doing it based on the final card that was drawn in the battle, because that is the final drafting decision card that was most proximal to the win or loss. So really what we want to do is allocate award updates based on that timeline. And then we can go back in time based on the order the cards were drawn, and then map those reward adjustments to the original drafting decision time points. So this next important limitation, the draft order and the draw order are not the same. The approach that I took to address these two problems is to reframe how reinforcement learning was applied to this task. So the general case of the problem is that there is temporal decoupling between the decisions and the effects of actions. In this specific case, there is a distinct decision phase where all action decisions are made, and then a distinct effect phase where all of those decisions then have their effects sequentially throughout the battle that is used to evaluate the agent's episode. I'm also making an assumption here that I can treat draft and draw time steps as equivalent. That is, each observation and action in the drafting phase can be mapped to individual draws off of the top of the deck. This doesn't necessarily hold because there are several other actions that happen in between draws during the battle, which are time steps in that environment. And also multiple cards can be drawn in one turn, some other complicating factors there. But I'll ignore them. And then the original authors trained a few different types of models with different neural network architectures. I focused on replicating and extending results for their LSTM-based model. I chose the LSTM model, which is the line in red, for a couple of reasons. So first of all, the first graph is the win rate of the first player network. It's higher than the win rate of the second player network because of first player advantage. And then there's an average, which I care less about for this work. So there were two interesting things about LSTM. If you look at the second player win rate, one, in both cases, LSTM performed worse than immediate, which was a simpler algorithm that was just looking at the current state and not considering history. So LSTM had more room to improve, potentially, but also that for the second player network, there was quite a bit more variance, which suggested to me that the agent might not be learning consistent amount of information with each update, and that was another area for improvement. So how do we map these two different timelines together? Well, if you look at the update algorithm for PPO, you have the generalized advantage estimate, which is comprised of the reward that was observed, the time discounted value estimate of the new state minus the value estimate for the current state, plus the time discounted and lambda multiplied and advantage estimate for the next time step. And this is an algorithm that can be applied starting with the observed reward and moving backwards to the beginning. So first, on the very last time step, the reward term will be the plus or minus that was observed. There aren't any t+1 steps here, so those terms are gone. And then the value term actually comes from the value that was estimated during drafting. But this advantage estimate is applied to the decision to the drawn card. Then for the next time step backward, the advantage estimate factor at the end of the equation is coming from that advantage that was estimated for that last drawn card, and the time discounted value of the next state time step is coming from the drafting timeline here. So they're coming from two separate timelines. Then the value of the current time step is again coming from the drafting, where there is no more further rewards, but if there were, it would be coming from the draw step during the battle. You repeat this process, mapping the two timelines together, and that is how you produce the rewards. You then use these to update the model while preserving the order for the drafting decisions. This is important for history considering agents or models such as LSTM, and also masking out any undrawn cards. So the implementation involved updating both the PPO algorithm and updating the training script. So first we had to add some tracking to be able to map effective steps, the steps from the draw phase, back to their corresponding steps from the drafting phase. We also need to track any masking for steps which should not be updated. Then we need to change the algorithm that computes the generalized advantage to incorporate this new mapping. And then for the training script, we need to add during one of the callbacks, logic that at the end of an episode calculates what that mapping needs to be. So how did this work? So first I wanted to recreate the original results. They didn't match exactly. The main reason for this is that the original code base did not fully lock all of the randomness down to seeds, so it was not fully deterministic when you set the seed, and I had to update the code to fix that. But it's roughly the same results. It's close enough. Now, if we compare the different conditions that I applied, first, this is the replicated results where we're not masking undrawn cards and reward is being applied based on the draft order. This is the results when we are masking undrawn cards and we are applying the reward based on the draw order. So you see that there's an overall improvement, and also that the rate of learning increases, and the variance looks to be somewhat improved, although not as much as I was hoping. Now, there is one problem. That draw condition is actually doing two things. One is it's masking undrawn cards, and two is it's reordering to match the order in the draw. It could be that one or the other of those is actually contributing to all of the improvement. So I did another condition, which was leaving the cards in the draft order, the original draft order, but then masking the undrawn cards. So the only effect should be teasing out the influence of giving award or punishment to cards that we never learned real information for, but not the ordering. And it looks like that actually is explaining pretty much the entire effect. So that means that the reordering to allocate the appropriate amount of reward didn't seem to contribute additional information. I wanted to look into that a little bit more, so I did one additional condition, which is instead of, so that in this final condition, we also are masking the undrawn cards, but instead of doing either the draw order or the draft order, we're going to do an entirely random order, just to see how the ordering is influencing things, if it's influencing things at all. And it looks like even with a random order, it has about the same performance. So the ordering doesn't seem to be having really any additional contribution to learning. So the findings from this show that excluding undrawn cards from updates works, which makes sense. We're no longer misattributing reward or punishment to cards that never had an influence on the evaluation. And calculating updates based on draw order doesn't seem to work. Why is that? I can think of several different reasons. So one is that the environment structure might be playing a role. Excluding undrawn cards may saturate the useful information so that there's not much more benefit in the additional information from the ordering. It could be that the game is either too short for that ordering to actually matter. The first and the last could just be close enough in value that it ends up washing out. Or it could be insufficiently complex, so that the order in which cards are played throughout the game is not having enough of an influence on the final outcome. It could also be that the game is too complex, so that the interactions between cards matter far more than the actual order that they were drawn and outweigh those factors. It could be that the battle agent that was used was insufficiently sophisticated to take advantage of that information. And it could also be that assumption about the draw and draft time steps was invalid, and that if you mapped if you use the actual more granular time steps from the draw phase, from the battle, that it would perform better. It also could be that I didn't do any hyperparameter retuning when I applied these new conditions, and that the additional information from the ordering could have been used better with a retuned model. It could also be that I made mistakes in my implementation, or that my theory is wrong.